So we proved that every finite dimensional vector space has a basis. This is what we are. We defined a vector space to be finite dimensional if there exists a finite set of linearly independent vectors which also span the whole of the vector space. And in that case, such a set is called basis. We have also proved that any two bases have the same number of elements. Now, in this sequence, we also have proved that how to obtain a basis. And for that, what we have used as such is to find out a linearly independent set of vectors. So let me recall what we have done so far in this context. So we proved that if V1, V2, Vn are linear are vectors in V, so they are either linearly independent, and in case they are linearly dependent, then some Vk should be linear combination of the preceding ones. This we used to prove as a deduction that if V1, V2, Vn are vectors in V and W is a subspace, which is the linear span of V1, V2, Vk, out of which V1, V2, Vk are linearly independent, then we can find out a subset of the original set V1, V2, Vn, which retain V1, V2, Vk, and also few more possibly of linearly independent vectors, and they still span W. So that will give that how to obtain a basis from a set of linearly independent vectors in V. We have proved that if V is a finite dimensional vector space, then it contains a finite set of linearly independent vectors whose linear span is V, whole of V itself. And as we have defined, if you recall, vector space to be finite dimensional, if there is a finite set of linearly independent vectors spanning whole of V, and such a set is called a basis. We proved that if V1, V2, Vn form a basis for a vector space V over F, and if there are m linearly independent vectors, then these in number, that means m, cannot exceed n. And if so, there are two bases having m and n number of elements. This argument can be used to prove that m is lesser or equal to n, and by interchanging, of course, the vectors vi's by wj's, you can also prove that n is lesser or equal to m. So that will prove that any two bases have the same number of elements. Once we know that for a finite dimensional vector space, the number of linearly independent vectors that span whole of the vector space, that means the number of elements in a basis. And since any two bases have the same number of elements, this number can be therefore given a name. And what name it is given? The dimension of the vector space V over F. So what is the dimension of V over F? Is the number of linearly independent vectors which span whole of V. That means the number of elements in a basis. And naturally, you can also prove that Rn and Rm are isomorphic if and only if m and n are equal. Also, for a finite dimensional vector space of dimension say k, it is always isomorphic to Fk. And converse also can be proved if the two vector spaces have the same dimension, they are isomorphic. Conversely, if they are isomorphic and finite dimensional, then they have the same number of elements in the basis. That means their dimensions are also same. Now, one thing can be proved is what is called as blowing up That means if you have a finite dimensional vector space V over F, and if there is a linearly independent set of vectors, say V1, V2, Vm in V, which are linearly independent, then if required, you may adjoin to this set a few more vectors such that this mu becomes the basis. That means V1, V2, Vm, and if needed, then Vm plus 1, Vm plus 2, Vm plus R is a basis. So how do we do that? If there is a basis, then these definitely do span and they are linearly independent. Let us say n in number. Then put all of them together. They also will span the whole of the vector space V. And therefore, there is a subset of these which retain V1, V2, Vm, and a few from the remaining ones. Call them Vi1, Vir, and these can be named as Vm plus 1, Vm plus 2, Vm plus R. So that this new set becomes a basis. So in a sense that we have extended this given set of linearly independent vectors so that we get a basis having these elements also in the basis. Now, a few results about the homomorphic images of the finite dimensional vector spaces, say V. So we begin with this observation. Let us say V is a finite dimensional vector space. So V over F would be a finite dimensional vector space over, let us say, F. And suppose W is a subspace. So if W is a subspace of V, then the first thing is W is also finite dimensional. Also the quotients we can also talk. So V, and you can say that the quotient space V by W are finite dimensional vector spaces. Moreover, what we can see is about the dimension of the quotient V by W over F is actually the dimension of V over F minus dimension of W over F. And if you want to prove, the proof is also rather simple. So the first thing is that V is finite dimensional. So let us take that the dimension of V over F be n, and this is finite. So what we know is that the number of linearly independent vectors cannot exceed n. So since number of linearly independent vectors in V over F cannot exceed n. So in particular, if there is a number which is more than n, then it cannot exceed. So let us take that. So what we want to prove that V, if its dimension is n, W is a subspace of n, V, then the dimension of W, first of all, cannot exceed n. And in that case, naturally, this will be finite dimensional vector space. So we can find out, so let the largest linearly independent set of vectors has m number of elements. So let us say that this W1, W2, and let us say Wm be the largest set and be a largest set of linearly independent vectors in W. Elements of W are elements of V, and V cannot have more than n linearly independent vectors. And therefore, this number m cannot exceed n. So we have got a linearly independent set of vectors in W, which are m in number, namely W1, W2, Wm. Now, if they also span W, then this becomes a basis for W. So let us take that this BW is, so BW is W1, W2, Wm, and this is largest possible set of linearly independent vectors from W. That means if there is some other set of linearly independent vectors from W, then the number of elements will not exceed m. So we claim that BW is a basis for W over F. Now, BW already consists of linearly independent set of vectors from W. So what we need to prove is that this spans BW spans W. So for BW spans W over F, let us take that this small w is an element in W. But then W together with these Wi's, these vectors are m plus 1 in number, but the linearly independent vectors in W can be at most m. Therefore, these should be linearly dependent. All of them are in W, must be linearly dependent. If they are linearly dependent, and so there exists a linear combination, say this alpha W plus alpha 1 W1 and say alpha m m0. Alpha and alpha i's, they are coming from F, where not all the coefficients, say alpha, alpha 1, alpha 2, alpha m are 0. Further, this alpha cannot be 0. For alpha is equal to 0 will mean that this linear combination will give me alpha 1 W1 plus alpha 2 W2 plus alpha m Wm is equal to 0. Now, Wi's are linearly independent. So what we get is each alpha I is 0. But then all alpha as well as alpha i's are 0. And this is a contradiction. Because we have assumed that not all are 0. We assume not all are 0. So is a contradiction. That means what? That alpha is not 0. So alpha is not 0 in F. This implies that alpha inverse exists in F. But this gives that W is a linear combination. So if alpha is not 0 and if you put here, then this gives that W can be written as beta 1 W1, beta M Wm, where beta I is minus alpha inverse alpha I is in F. So it's a linear combination here of W1, W2, Wm. Hence, BW is a basis. So we have obtained a basis, so BW having m number of elements and m is less or equal to n. So now BW is a basis for W over F. Number of elements in BW is m is less or equal to n, which is the dimension of vector space V over F. So this gives that your dimension of W over F is less or equal to dimension of V over F. So this is what is the first part. Now for the second part, recall that the quotient space. So V by W consists of what? So this consists of the cosets V plus W. V comes from. Now this is a vector space with respect to the coset addition, and the two cosets is a vector space over F. Recall also the few things that the two cosets this are equal if and only if V1 minus V2 this belongs to W. Addition of two cosets is V1 plus V2 plus W, and the scalar multiplication of these alpha times V1 plus W alpha V1 plus W. So with this addition and scalar multiplication, this V over W becomes a vector space. We say that this is also finite dimensional, and we obtain a basis therefore for W, V by W. So since dimension of V over F is n is finite, so So we get that the dimension of W over F, let us say M, is less or equal to N is also finite. That is what we have proved. Now dimension of W over F is N, so let us take a basis for W over F. So let us take, say, BW. BW consists of W1, W2, and these are in number Wm. Be a basis for W over F. All right, so what we can do is that we can blow the set BW so that we get a basis for V over F. So blow the set BW so that B, and this is W1, W2, and let's say Wm together with the few, if required, V1, Vr is a basis for V over F. So that is what we said, that if we have a linearly independent set of vectors, we can adjoin. Blowing up means we can adjoin few more vectors if needed from the vector space V over F, so that this new set, which retains these linearly independent vectors, together with few more if needed, becomes a basis for V over F. Okay, so suppose this is blown to B so that B becomes a basis. So now BW is a basis for W over F, B is a basis for V over F. Now let us take the quotient space, say V by W, and what we see is here. So any element of the quotient space V by W will be a coset V plus W. So let us take V in V. So this means that V can be written as a linear combination of these vectors. So this is alpha m w m plus beta 1 v1, beta r v r. Alpha is beta j's are from F. So this is a linear combination of these vectors. So what we get now here, so V plus W, coset of this is the coset here, alpha 1 W1 plus alpha m Wm plus beta 1 V1, beta r Vr. बाहर हो गया, this W. So this is same as the sum of the two cosets. So this is one element, say U1, this is U2. So this is alpha 1 W1 plus alpha m coset of this together with the coset of beta 1 V, beta R V R plus W. Now this is an element of W, and therefore this whole thing is the coset W. So this makes, therefore this is equal to, so this whole thing is equal to, so V plus W is equal to, so W for the first one plus, now you have here, so beta 1 V1 beta R VR plus W. So this is same as the beta 1 V1 plus beta R VR. And once again, if you use the two, how the addition and scalar multiplication of cosets is defined, then this is the coset plus W beta R VR plus. So if you take, say, for example, now we observe that set, let us take beta bar. This B bar is the set which consists of these cosets V1 plus W, V2 plus W, VR plus W. So they span the quotient space V by W over F. We claim that this is a basis, in fact. What we claim is this B bar is a basis. V over. Now since these sets which are cosets here, the elements, so these cosets are spanning whole of V by W. The only thing for that remains is to prove that these are linearly independent. So for that we need to prove that the cosets is a linearly independent set. When we say the set is linearly independent, it basically is to say that the elements in the set are linearly independent. So suppose there is some linear combination equal to 0, we would try to see if the coefficients are 0 or not. So let us take some linear combination, say of V1, V2, VR. So let us take, say, gamma 1, V1 plus W, and so on, gamma R, VR plus W. This is 0. This is 0. Here, 0 means 0 of V by W. That is W. Where for some, the coefficients gamma 2, gamma R are from F. So what we want to see that these coefficients gamma 1, gamma 2, gamma R are 0 or not. So suppose this linear combination of cosets is 0. What does it mean? What does it mean is that the way the sum and the scalar multiple of two cosets is defined. So this makes that this is gamma 1 V1 plus gamma 2 V2 gamma R VR this plus W is 0 of V by W, that is W. Now these are two cosets here. So that makes that gamma 1 V1 plus gamma 2 V2 and plus gamma R VR. This belongs to W. Now, if that is the case, since BW, which is W1, W2, Wm, is a basis for V over W over F, what we get? That this element here, V gamma 1 V1 plus gamma 2 V2 plus gamma R VR, is in the span of BW. So we get therefore the scalars, so say delta 1, delta 2, delta M in F, such that. So gamma 1 V1 plus gamma 2 V2 plus on gamma R VR is equal to delta 1 W1 plus delta 2 W2 and this is delta M WM. So what does it make that this is a linear combination and push everything on one side? What shall we get is, so this makes, so this implies that so delta 1 W1 plus delta 2 W2 plus delta M WM plus, so is here minus of this gamma 1 V1 plus minus of gamma 2 V2 and plus minus of gamma R is equal to 0. Now since B, which consists of these W1, W2, Wm, together with V1, V2, Vr is a basis for V over F, the vectors W1, W2, Wm, V1, V2, Vr are linearly independent. And so we get each coefficient is 0. So delta 1, delta 2, all of them, delta M minus gamma 1, minus gamma R, all of them are 0. So minus gamma 1 is 0, gamma 1 is also 0. So that makes each delta I and each gamma j is 0. This proves that so in particular this V1, V2, VR are such vectors that their cosets are linearly independent. So this proves that V1 plus W, V2 plus W and VR plus W are linearly independent in V by W over F. The span V by W that we had seen, and that makes that this is now B bar, these are the elements of B bar, is a basis for V by W. V by V by W. So the dimension here of V by W is, so the dimension of V by W over F is R. R is simply N minus M. N minus M, so this is dimension of V minus dimension of W. So that's what we have proved. So the dimension of the quotient space is the difference of the dimensions of the vector space and the subspace. So as a simple observation from here, we can also prove a little more. So this gives that, so let us take say W1, W2, the subspaces of a finite dimensional vector space, say V over F. Then each of these will be finite dimensional. So W1 plus W2 and W1 intersection W2, W1 plus W2 by W2. This becomes a quotient. And W1 by W1 intersection W are or is also finite dimension. Moreover, what we can see is that the dimension of this sum W1 plus W2 as a subspace is actually the dimension of W1 over F plus the dimension of W2 over F. So for the proof, the simple thing is as follows. Since W is any subspace W of finite dimensional vector space is finite dimensional, and therefore the dimension of W1 is finite, dimension of W2 is finite, the quotient space W1 by W1 intersection W2 is finite. So for the first one, that this W1 plus W2 is also finite dimensional. So for that, what we use is this simple thing. So recall that the isomorphism theorem, that W1 plus W by W2 is isomorphic to W1 by W1 intersection W2. Now W1 plus W2 is both, so this will give that the dimensions of both sides must be equal. So the dimension of W1 plus dimension of W1 plus W2 by this say W2 is same as the dimension of W1 by W1 into over F. Since everything here is finite dimension. Now use the dimension of V by W is dimension V minus dimension W, so that the left hand side is the dimension here W1 plus W2 over F minus dimension W2 over F is same as dimension over F of W1 minus dimension of W1 intersection W2 over F. So you can therefore shift this dimension W2 on the right hand side, and this is dimension of this sum 1 plus W2 over F, same as dimension W1 over F plus the dimension W2 over F minus the dimension of the intersection over F. So this is what we get here because of this. So whenever there are finite dimensional vector spaces, we can have observations about these subspaces, the quotient spaces, homomorphic images. Of course, the isomorphic images will have the same dimension. We would now like to discuss the vector spaces which are of interest to us, say just a minute. Okay, so okay, some interesting vector spaces we want to see here. So what is called as the dual spaces? So let us take the vector spaces V and W over the same field, say F. So let us take for the dual spaces. So So let us take V is a vector space over F and W is also a vector space over F. So be vector spaces. Now define here symbol say home B W for F. To be the set of all homomorphisms of V into W. So this is the set here of all homomorphisms of. So T is a homomorphism of V into W. Now we want to make that this is a vector space with respect to some addition and scalar multiplication. So for this and for any T1, T2, let us take here T1, T2 in this home V W. So define the map for T1 plus T2 from V to W. That takes V to V under T1 plus T2 defined by say V T1 V T2. So define like this and also the scalar multiplication, the map and for every alpha in F, the map alpha T is from here V to W. So this V going to V under say this is alpha T is same as here alpha and then this is V under T alpha V. So define the two operations now, the addition and the scalar multiplication on elements of home VW. What does home VW consist of? It consists of the homomorphisms of V into W. Now, each of them, first of all, that the maps are well defined, that is for you to prove. And the second thing is that T1 plus T2 alpha T, both of these are elements here in VW, home VW. That is what, that this is closed. Other properties one can verify. So let us take now. So now T1 plus T2 is well defined and also that T1 plus T2 and alpha T, they are here in home V W over F for every alpha in F and for every T, T1, T2 in home V W. For so T1 plus T2 is a homomorphism, so one has to prove two things. So for T1 plus T2 here in home VW. So observe for let us take two vectors to say. So this must be a homomorphism. That means it should preserve addition and scalar multiplication. So you can take let us take two vectors V1 and V2. So for V1, V2 in V and beta in F. So V1 plus V2 of T1 plus T2. Now how did we define that? This is V1 plus V2 under T1 plus V1 plus V2 under T2. And this is T1. T1 is a homomorphism, and therefore this is same as V1T plus V2 T1 plus V1 2 plus T2. Now V1 T1, V2 T1, V1 T2, V2 T2, all of them are in W. All these elements are in W. W is a vector space over F. Now once we say it's a vector space over F, that means W is an additive abelian group. So all of these can be written in this order also. So you can now write that this is V1 T1 plus V1 T2. This is V1 T1 plus V1 T2 plus V2 T1 plus V2 T2. The first one is V1 under T1 plus T. The second one is V2 under T1 plus T2. So T1 plus T2 preserve the sum. We can also prove that this is the first thing that T1 plus T2 preserve sum. You can also check that beta V under T1 plus T2. So beta here V under T1 plus T2. This is same as beta V under T1 plus beta V under T2. So this T1 is a homomorphism, so this is beta V T1 plus beta V T2. This is same as beta V T1 plus V T2. And this is same as B under V under T1 plus for every beta in F and for every V in V. So this proves that T1 plus T2 preserves the sum and scalar multiplication, and hence T1 plus T2 is a T over W. Now, similarly, you have to prove that similarly for every P in the homomorphism V2W, and for every say beta scalar or in F, alpha T is also a homomorphism of V. So once you prove this also, then what we have proved that home VW is closed, proving that home VW over F is closed with respect to addition and scalar multiplication. So in fact, you can prove that this home VW is a vector space. So we shall in the next lecture try to see what could be the dimension of this new vector space, which is obtained from the homomorphisms of V into W in case both V and W are finite dimensional vector spaces, and we shall prove that the dimension of only W over F is the product of the dimensions of V and W over F. So we close it. Thank you very much for your kind attention.
Thank you, sir.